afternoon, everyone. Welcome to Optimizing Performance Without the Price Tag. My name is Dharmita and I will be sharing the stage with my colleague, Daka Jung, today. This is our first time at Dash, and we are really excited to share with you our findings using OpenTelemetry and Datadog APM. We've spent the better part of our careers in performance engineering, and there is a subtle but important difference between performance testing and performance engineering. So show of hands if you've ever have applied load to a system, if you've done any kind of performance testing. Okay, good. A few of you, a lot of you. So performance testing is a component of performance engineering. Performance engineering is more of a holistic approach. And that's really the premise of our talk today. It's to try to understand the factors that limit scalability and thereby increase costs. So Splunk actually explains this process really well on their website. Performance testing is nestled there in the coral between performance architecture, requirements, performance modeling, or personas, analysis, and monitoring. The performance engineer may look at a high response time and wonder if we need to look into code profiling, database optimization. They may look at the architecture and suggest architectural changes and look at how the load is being applied. Are we using API testing? Are we using front-end testing? So it's a really tedious discipline, especially with complex distributed systems as we have now. So what will we be covering today? Today we'll show how we use Datadog APM traces to understand code inefficiencies. We'll talk about how we discovered N+1 anti-patterns, as well as the open session and view anti-pattern. We'll also talk about how we were able to get to the root cause of excessive calls in our database. In our code base. We then used Datadog database monitoring to quantify the impact of these findings. And we used OTel metrics. We pulled OTel metrics into Datadog, and those metrics informed our tuning for our database connection pools. So we'll cover all that today. Why do we need to do this? Well, we have a lot of microservices, and we have a large footprint. And we want to delight our customers, but not be responsive by scaling a bazillion replicas of our services. So in each of the examples that follow, we'll show how efficient code and targeted tuning can lead to reduced resource utilization, which directly impacts cost. So I have a couple of slides just to set some context before we get into the nitty-gritty technical details. SAS is a privately held analytics company in Cary, North Carolina. Next year, 2026, marks our 50th anniversary. We have a gorgeous campus, and the sheep there tend to the grass on the solar farm that's on campus, where I like to jog sometimes. And we have lots of fun get-togethers where we can see folks that are remote or even in other buildings that we don't see often. Baya is a software stack that we'll be discussing today. It's a cloud-native AI and analytics platform, and it supports all of the steps of the AI and data lifecycle. It supports data preparation, visualization, modeling, and decisioning. Here are a few examples that are under the VIA umbrella. So for example, SAS Model Manager is an application in the VIA umbrella, under the VIA umbrella. So a model in banking might give you the probability of someone defaulting on a loan. Model Manager is a generic tool that helps track the performance of these models and also acts as a repo for these models. Our customer Disney might use SAS Model Studio to create a model to target promotions for their customers. this is the software stack that Via uses. Via runs on Kubernetes in the cloud. The focus of our talk, even though there are a lot of layers here, the focus of our talk will be the microservices and their interactions with the shared Postgres database. As I mentioned, we use OpenTelemetry with Datadog. So this is a screenshot of the Datadog software catalog with the Via microservices that are in this particular deployment. Here we see we have 104 microservices. We have a mix of Java and Go. And we have instrumented 87 of the most interesting ones. So we have 62 microservices in Go, 24 in Java in this particular deployment. OTel is an observability framework. It's used to standardize instrumentation, collection, and export of telemetry data. So here's just a sample of what a Java microservice instrumentation might look like. The yellow arrow shows the initialization of the Java-specific OpenTelemetry SDK. The exporters for traces and metrics, and we use the OTLP protocol to export our trace and metric data. And the blue arrow shows how we can extend this instrumentation. For example, if we were interested in learning more about Hibernate. There's no OTel collector in this mix. Datadog agents are running on our Kubernetes nodes, and they ingest all the OTel data. We also have Datadog infrastructure monitoring on this one cluster that we have set up for this. The microservices are deployed, like I said, with Kubernetes across multiple nodes on Azure. And the arrow here shows the model manager service that we discussed in the earlier examples as an example application under the Via umbrella. Besides the microservices, the other big component in our architecture that we're going to discuss today is the shared Postgres database. So for that, we have the Postgres integration, the Datadog Postgres integration, and we also have the Datadog database monitoring feature enabled. So once we started pulling in all this data, we pulled in the traces, and we pulled in, the integrations. We were integrating just with Postgres for this specific example, but we also have a RabbitMQ integration, and we have Nginx integration. And so we pulled in all the instrumented services, all the discovered services, all the instrumentation, and this is a flow map in Datadog of our one Via test cluster. It was complicated. Showing all of these dependencies made us realize the complexity of the entire system as a whole. So within R&D, which is where Daka and I work, we have OTel adoption, but we didn't really have deep observability that Datadog provides. So our senior leadership recognized the complexity with all of these dependencies, and they sponsored an R&D-wide collaboration. We called it an expedition because our charter was to go find performance problems. I got to lead this expedition team, and we had a mix of product and core services represented. We also had a mix of performance engineers, developers, and DevOps represented. Now, as I mentioned, we are in R&D, and we're a bunch of introverted people. We are nowhere near as excitable as the people in this stock photo. But the nice thing about working with developers is that they have a sneaking suspicion of where all the problems lie in the code. So that's going to bring us to our first case study. This is the N+1 problem. So the N+1 problem we typically see with Hibernate and Java applications. Hibernate simplifies the interaction between Java objects and relational databases. It makes life easy for the developer, but it has the ability to unleash a massive amount of database queries. The problem is that without observability and without some load or data in the system, it's very hard to detect some of these problems. So let's split up N+1. The one part is the initial query to retrieve a list of objects, and then you have to issue n more queries for each of the properties of those objects. So the analogy would be, imagine you're leading a school trip. You go to the front office and you say, how many kids are going on this trip? And the front office says 353. And imagine if you had to go back into the school, and for each child that was going on the trip, you had to retrieve their property or their backpack. It's going to take a really, really long time to get those buses on the road. So our specific example for N+1 is with this Moz service. This is a screenshot of the trace for the fire synchronization tasks method, which is a method within the Moz service. And the one part there shows that initial call to fetch a list of modules. And then there are 2n more queries, because there are 2 properties per module. So we now have 2 times 353, because there's 353 rows in the database, queries made in order to fetch all the properties for these modules. So of the 1,000 or so spans that are in this particular method, 70%, or 707 of them, are to fetch properties from a database. Now you can see how this problem would increase even further if instead of 353, we had 500 or 5,000 modules in the database. Further compounding the problem, this is a Trace Explorer view, we were able to see the sheer frequency at which this call was executing. The fire synchronization tasks method was running every 10 seconds, and each call had over 1,000 spans. When we looked closer at the method, at the service, we found 2 other methods that were also exhibiting the same N+1 issue: the collect and publish and the process pending jobs. They were also running every 10 or 20 seconds. So we understood the problem for the microservice standpoint. And this is a screenshot of DBM, which is a database monitoring feature within Datadog. We wanted to understand the aggregate impact of these queries on our shared database. So what we learned once we turned this feature on is that we were just hurling queries at the database. In a 10-hour period on a mostly idle system, 3.62 million queries against the module step table, 3.62 million queries against the module property table, almost 1 million queries to the module info table. One thing I want to note is because we're using Datadog APM with OpenTelemetry, there is no connection between APM and DBM. We had to manually stitch some of this together, but hot off the press is that there will be support for APM with OpenTelemetry and DBM. So that'll be really great because it'll help us make these findings much more easy. Datadog's observability made a compelling case for the developer to make some code changes. It was nobody's fault. The code had changed hands 4 times. But the developer was able to review the data access patterns, and he made the fire synchronization tasks method much more efficient, and he also eliminated calls that were being generated from the other 2 methods. This led to astounding optimizations. If you look at the rows, the 3 methods that had the N+1 problem, for example, the last one, the fire synchronization task, we went from 1062 spans per call to 3, which was a 345x improvement in the number of spans. And we were calling that method a lot less frequently. So tying all of this back to the premise of our talk, how does performance optimization impact the price tag? When we looked at the resource utilization for this particular microservice, once the fixes were pushed, Moz consumed 4 times less CPU than before. And being able to see the system as a whole really allowed us to connect the APM trace data to the resource utilization. Additionally, Moz is also putting a lot less burden on the shared database. So for the next example, I'm going to invite my colleague Daka Jung on stage to talk about how she used APM traces to dive into excessive calls. Sorry.
Thank you, Dharmita. Hello, everyone. I'm Dr. Zheng. It's been an exciting journey with Dharmita and our expedition team to uncover performance bottlenecks using OTel and Datadog's visualization tools. Today, I will share 2 case studies to highlight the impact, starting with how APM traces help us reduce excessive calls. In a 20-user load test across 25 services, we found that the get folders endpoint of the SAS file store service had a P90 response time of 1 minute and 33 seconds. Why is it so slow? We began the investigation by looking at the APM traces and find that 99.4% of the time was spent in SAS authorization, as shown in the flame graph on the left. The waterfall view on the left showed that the majority of the time was consumed by the authorization decisions call. This APM information helped us quickly pinpoint the problem. The API authorized every folder ID in the database, not just the 20 records being returned. With over 4,800 folders in our system, this unnecessary authorization process caused major delays. We collaborated with developers to change the API to authorize only the returned records based on the starting position and limit size. The results? Staggering. The authorization calls were drastically reduced, and the API response time dropped from 93 seconds to just 396 milliseconds. That's a reduction of 235 times. Beyond just speed, the resource usage of this service was significantly improved. CPU usage dropped from 7.2 to 2.1 millicores. That's a reduction of 3.4 times. Memory footprint shrank more than 100 megabytes. That's 2.3 times saving. Meanwhile, network throughput greatly increased, suggesting more efficient processing. Because SAS authorization is a centerpiece of VIA, essentially every service API call needs to be authorized. This optimization significantly boosted the overall application performance. That's the kind of powerful insight and impact APM tracing gives us. For my second case study, let's dive into Open Session in View. Earlier, Dharmita shared the N+1 problem. OSIF is another untyped pattern we tackled. What is Open Session in View? OSIF is a commonly used pattern in Hibernate Spring Java applications where the database connection stays open for the entire request lifecycle. While this may simplify coding and lazy loading scenarios, it causes inefficiencies and performance issues. Ideally, we want to keep the database connection open only for the duration of database operations and exclude other I/O activities from the connection session. However, when OSIF is enabled, as shown in the bottom part of this graph, the connection remains open for the entire request processing phase, including both database queries and non-database related I/O activities, such as remote service calls. This prolonged connection holding could cause congestions of the connection pool, limiting overall transaction throughput, and forcing other concurrent requests to wait for a connection. Consequently, during periods of high workload, JDBC connection shortages might occur. To visualize the connection pool usage, we instrumented OTel in Java pool options of our Kubernetes deployment for get, create, and return connections. Get connection is called to lease a connection from the pool. When there's no idle connections available, and the max active limit has not been reached, create connection is evoked to open a new connection. Once the request is complete, return connection releases the connection back to the pool. Among these three calls, create connection is the most resource-intensive operation, usually taking the longest. With this OTel instrumentation, we can see spans in the APM trace for get connection, create connection, and return connection. The duration of the logical database session is demarcated by spans from get to return connection, as shown in this brown bracket. When OSIF is enabled, we observed multiple remote service calls within this connection session, including the 2 authorization calls marked in red. Notice one of those calls took over a second to return, which means the connection was held open unnecessarily while waiting for the remote calls to complete. This is not an efficient use of the connection pool. When under load, this pattern causes latency in the system. With OSIF disabled, we find a very different call pattern. Instead of one long database session, the same API call now has 2 short and focused sessions, each used only for queries. The remote service calls now happen outside of those connection sessions, indicating more efficient use of the connection pool. Another takeaway, most of the get connection time is spent in create connection. This is true regardless of OSIF configuration, but when OSIF is disabled, shorter database sessions result in more reuse of the existing connections, thus reducing the need for those more expensive create connection calls. To evaluate the impact, we created metrics based on the APM trace. For instance, here's the span query for the get connection metrics. We then built a dashboard to track the connection pool usage for the count, average duration, and sum of duration for the get connection metrics shown in blue, create connection in orange, and return connection in green. We ran a microservice load test to evaluate the OSIF configurations, comparing OSIF enabled and disabled situations, and find that with OSIF enabled, the total time spent in get connection for the test was 1.46 minutes. Nearly all of that, 1.45 minutes, were due to 36 create connection calls, averaging 2.42 seconds each. With OSIF disabled, the total get connection time dropped to just 14.4 seconds. That's a reduction of 6 times. There were fewer and faster create connection calls, showing much more efficient use of the connection pool. In addition, OTel metrics showed that both the idle and used connection counts reduced when OSIF was disabled. This suggests that the connection pool handled the same traffic with fewer connections, thanks to shorter lease durations, increased connection reuse, and reduced pool congestion. In summary, OTel instrumentation allowed us to quantify the performance impact of OSIF. Based on these results, we're now evaluating OSIF disablement with over 20 other Java services in VIA to ensure scalability gains without any functional regressions. With that, I'll hand it back to Dharmita to dive deeper into OTel metrics. Thank you.
Thank you, Daka. So Daka demonstrated how she was able to use spans as metrics. At this point in our expedition, it was abundantly clear that we were chasing problems between our microservices and access to the shared database. Access to the database was the bottleneck. Our developers were really curious, how can we get to the bottom of this? And so next, I'll talk about OpenTelemetry and how we were able to use OpenTelemetry to inform our tuning decisions. So just to recap, metrics are just measurements that are captured at runtime, summarized and reported periodically, CPU, memory, requests, errors. OpenTelemetry are a little bit different. They are ingested separately and enabled separately from traces and logs. So if you recall, the early slide where I showed some of the Java microservice instrumentation, we had a -d flag, a -d for OpenTelemetry exporter, and it was set to OTLP. That's how we're exporting OpenTelemetry. The other thing to note is that OpenTelemetry are mapped to Datadog. And the reason I mention this is because early in our process, we ran into an issue. And the issue was that OTel was sending metrics with a prefix of jvm.star. Datadog was expecting process.runtime.jvm.star. It was okay for us because what we had to do was work with our account executive, work with our engineers, open a support ticket, and explain the issue, get the ticket resolved, update our agent, and adopt that new Datadog agent in order to get this metric mapping correct. But this is just something that we will have to keep an eye on as OTel evolves. OTel is changing, it is progressing, and Datadog's adoption of OTel is also increasing. Finally, with OpenTelemetry, we can have standard conventions. So the last bullet there, we don't have to roll our own. We don't have to have a SAS prefix on our metrics. We can actually just use the standard convention. So as I mentioned, our team, our expedition team, was deep into trying to figure out how can we get to the bottom of these issues. And what we realized was that for Go, we needed a specific instrumentation library, and it was called OTelSQL. It had the database metrics that we were looking for Go. For Java, we could just use the standard semantic conventions that came out of the box with the OTel Java library. What this meant was that in our metrics, there's different prefixes. So the Go metrics have the db.sql.star prefix, and the Java metrics have the db.client. So what did we learn using these metrics? Well, when we ran a 16-user concurrent user load test, and we followed a directive to go find performance problems, we created a dashboard with all of our Go microservices and the metrics that we had for them. In this particular dashboard, we can see that the database max open and open metrics look pretty good. The open, which is a green jagged line, is below the max open, which is a flat line. So for all of our database-intensive Go microservices, things were looking pretty good. But on the same test, using the same dashboard, we looked at one other metric. It was a DB SQL connection close max idle metric. And it was very high. We were closing over 1,000 connections a minute. So we had to dig into this, and what we discovered was that we knew that we had a shared framework, but we have a max idle connection setting that was the default across all of our Go microservices, and it was set to a value of 2 for all of our connection pools. That means that we can only have 2 connections waiting to accept work. It didn't matter if we had a pool max of 10 or 20 or 50 connections. We can only have 2 idle that are waiting to accept work. Our developers came up with this clever animation to explain this thrashing problem. So when clients request connections and we have idle connections, we provide the connections. When we're out of idle, we have to create new connections. And we just learned from Daka's presentation that creating and opening connections is expensive. So if we pay attention to the green tally marks, we've opened connections. Now, when we are finished with the connection, we return them. And we have to close the ones that exceed 2 because we can only have 2 idle at any point in time. So now when we need connections, we have to create them again. And when just moments ago, we had a connection available. So we now understood the high rate of thrashing. It's just fun to click these dots. So once we understood the issue, we began experimenting with the max idle connection metric, our tuning parameter. And we ran 2 tests, T1 and T2. T1 had the new setting with a value of 10 for the max idle connections. T2 had the original setting. And so we can see in the top graph that for this one service, the max open connections is equal to the open connections for T1, which has a new setting. And in the graph below, we can see that we no longer see the thrashing due to the aggressive connection closing in T1, like we had with T2. And these are tests that were run, it's the same 16 concurrent user load that we were running for both tests. So things were looking better. We were also able to see that with T1, which is a new setting, we had reduced wait time to obtain a database connection. That wait time was reduced to 1/3. Additionally, the HTTP server request duration also was reduced. So we learned that we have to have connections available to use to impact performance, but we have to be careful because these are settings. This is one microservice. We have, in this deployment, 62 Go microservices. And these are connection pool defaults for all of them. So what we learned is that in addition to having the max idle connection value changed, we also need to set a timeout so that we're not inadvertently impacting the shared database by keeping connections open when they shouldn't be. And you might say, well, duh, of course you needed a timeout. Why didn't you think of that? The problem was that the connection pooling was added back in 2019. But this connection max idle time, which allows you to set the timeout, wasn't added to Golang until the following year. So we had to discover that and then adopt it in order to make sure that our connection pool tuning was valid for all of our services. So again, coming back to resource utilization. This is a screenshot of the Kubernetes CPU usage for that one database service that we were tracking. And here we can see that once we push the changes in T1, we're using half the CPU as we were with T2. So in T2, with a max idle connection setting of 2, we were using 477 millicores, and we're down to 200 millicores, again, running the same 16 concurrent user test. When we apply these changes across all of our database-intensive services, the savings in terms of resource utilization are pretty impactful. So we're almost at the end of our talk, and I have 2 takeaways. One is on the process, and the other is just summarizing our findings. So a lot had to come together for us to have these findings and to be able to make the recommendations and make the changes and evaluate the impact. I'm going to go left to right, top to bottom. First, our senior leadership had to recognize that this collaboration was necessary, that we needed to bring a lot of experts together. We needed an environment that was dedicated and customer-like. That meant provisioning infrastructure that was right-sized so that we're not testing in a constrained environment and chasing artificial issues that wouldn't really arise in a production environment. We also had to have a representative deployment. We needed to make sure that our services and our applications reflected what a customer might do. We had a critical expert help us with our infrastructure and deployment. Second, observability. We needed to pull in addition to traces, OTel traces, we needed metrics. And early on, as I mentioned with the JVM runtime metrics, we ran into some issues. We reached out to our account executive. We reached out to the Datadog engineers. We opened tickets. We needed help in order to get this observability right. We had to collaborate also with a multitude of developers to understand the logs. We pulled in logs, and the logs helped us identify gaps in our observability. What were we not surfacing using OTel that we should be surfacing? What was in the logs that should really be a metric? Additionally, we had to add custom instrumentation. Daka went over how we were able to use the get, create, return connection spans as metrics. Additionally, our developer also had to add the OTel SQL Go instrumentation library. The workload. We had to have representative artifacts in our environment. Without those 353 rows in the database, the N+1 problem for Moz might have been really difficult to surface. It's really hard for a developer to see that without observability and without data. Daka was able to dive into the authorization issues because there were 4,800 folders in our system. We had to construct relevant load tests. The 16-user, 40-user, 80-user load tests that had to have the infrastructure to support the client infrastructure to run those load tests. They had to be multi-step, they had to be representative, they had to run without errors. And finally, it's a critical error, critical mistake, to do all these other three components and not make the time for analysis. For us, that meant getting together, getting the expedition team together twice a week for a couple of hours, and using the Datadog notebooks and the dashboards, and digging into our findings and figuring out what our next steps were. Datadog is a phenomenal collaboration tool. We were able to function much better as a result of all of us looking at the same data at the same time. So again, the traces helped identify code inefficiencies. Metrics guided our tuning. Both of these led to efficient code and a more tuned system, which led to lower resource utilization, which helped us lower our costs. I hope some of these strategies inspire you to investigate these options to improve your performance without sacrificing, cost. So thank you so much, and we'll open it up for any questions. If you have a question, there's a microphone. I don't know if, you might have to.
Hi, I had a couple of questions. Sorry, too loud. So the first one was, how did you identify the threshold value of 10 in your T1 test case that you had just shown, right? You had a value of idle timeout of 2, and then you scaled it and you changed it to 10.
Yep.
How did you identify? Was this through a process of R&D and figuring out where should
Yes.
we draw the line?
Yes, that's a great question. So the question is, how did we figure out the right tuning value? And
Yeah.
with tuning, it is a process of trying different values. So we started with 0, 1, 5, 10, and determined that 10 was a good number for the number of microservices that we're trying to access our shared database, given the limitation on the Postgres side also on the maximum number of clients that could connect to it. And so it is variable based on the kind of load that your service might experience, but it was through experimentation is the short answer.
Okay, and then if you went about 10, did you see degradation in overall performance, or there was no improvement?
We did not try a value above 10. Just with the sheer number of microservices that we have, we wanted to be conservative in that.
Okay, thank
Yeah.
you. And then the second question was to Daka. The second experiment that you had conducted, you had shown that the create method consumed most of the time. But what I wanted to understand is if the connection remains open for a longer duration of time, and if there are multiple calls, maybe this is not in exactly something that you would have faced, but in the real world, if there are multiple connections going out to the database, if you keep the connection pool open, then you can have all of those requests being handled at the same time. However, if you close out the connection very quickly, then you will have more number of calls going out to the database to request for new connections. So how do you tackle that? Because looks like in the example that you showed that after a certain period of time there was absolutely no request going out to the database. But what if the database is very chatty and there is a lot of application calls going to the database? How do we tackle that?
I think it depends on the load and how you construct your queries and the data in your system. There are a lot of factors to determine whether the longer held connections is performing better or the frequent turnover of the connections would do better. Because with OSIF disabled, the shorter connection sessions actually resulted in more reuse of the existing connections. It's not opening new connections, but those connections in the pool are being used. So that process is fast. So yeah, that's our experience. We did some load tests to evaluate the performance impact of turning off OSIF and find that for one of the Java services, when OSIF is enabled, the system could support up to 44 concurrent users without hitting errors. Whereas with OSIF disabled, it scaled up to 54 users. So that's 23% increase in capacity.